it is a simple PN junction diode. Okay, LED means light emitting diode. Okay, diode which emits the light, that's it. Okay, this is PN junction diode, and it will work under forward bias condition. Okay, under forward bias condition. Okay, forward bias I am writing just FB. Okay, so it will convert, or it will emit the light, or you can say electrical energy to optical energy, or light energy, whatever you can say. Okay, optical energy. Okay, this is just we are regularly seeing this LEDs, so it is easy to understand concept also. Okay, just LED simple PN junction diode. It will connect, it will convert, or it will emit, whatever you can say, electrical energy to optical energy under forward bias condition. This is very simple definition. Okay, so this is the thing. Symbol is, it's just like a PN junction diode only, but here plus sign and here minus sign, it is emitting light, so you put arrow marks outside. Okay, arrow marks outside, this is a just symbol, and we'll see how it will work. Just we will take semiconductor and n type semiconductor, and we will make a junction. Okay, we will make a junction. This is the interface between two semiconductors. Interface between two semiconductors. Here we are taking p semiconductor. Here we can take n type semiconductor. So you can take first n, after p also you can take, but that is our convenient, whatever you can take. So first to understand easily, just I am drawing this band diagram at equilibrium condition. That means the Fermi level is constant throughout the semiconductor. Okay, that is for easy way I am explaining. Okay, that is constant throughout the semiconductor. Just you have drawn these two things. After that, for p type semiconductor, the Fermi level is close to the valence band. Okay, you draw this one, and conduction band away from the Fermi level. Conduction band is away from the Fermi level. So here same thing what we are discussing a few classes onwards. This is EC and EV. Here also for n type semiconductor, the Fermi level is close to the conduction band. Okay, that is and it is away from the valence band. Okay, this is the same thing, EC and EV. So our job is just you draw the energy levels, Fermi level, and you connect this. So Fermi, this p type semiconductor, it is receiving electrons, so downward bending. So n type semiconductor, it is leaving electron, so it is upward bending. Okay, here also same thing. If it is upward conduction band, how it will bend, the valence band also same bending will take place. Okay, it's someone is it's not different, so we know. But this is equilibrium condition, but we are applying forward bias condition. Okay, we are applying some forward bias voltage or forward bias condition. This junction is connected to forward bias. That means plus terminal is connecting to p side, and negative terminal is connecting to n side. Okay, this is called forward bias condition. When you apply forward bias condition, the Fermi level is no more constant. The Fermi level is not constant, because the carrier concentration in p side and carrier concentration in n side is changing. That's why the Fermi level here shift upside, and here in case of p type semiconductor, the Fermi level shift downside. Okay, that is what we have discussed several times. So we'll draw it again, that one. Okay, we'll draw that Fermi level again. Okay, just I am deleting that one, and we'll draw in forward bias condition band diagram. Okay. That means the Fermi level is here. Okay, towards n side here, and towards p side here. Okay. So there is a difference between the two energies of Fermi energies, or you can say energy difference is there. Some energy level difference is there in Fermi level of n side and Fermi level of p side. Okay, E F I am writing here. For p side, E F P I am writing. Okay, just to distinguish. Okay, now this is done. Okay, this is the depletion width. This is the depletion width. Okay, this is the depletion width. Okay, here once this junction is forming, we know here holes are the majority carrier in valence band of p type semiconductor. Okay, So in p-type semiconductor, holes are the majority. That free holes will exist in valence band. Okay. Next thing, free electrons are available in the conduction band of n-type semiconductor. Okay. In n-type semiconductor, electrons are the majority carriers. That free electrons will exist in conduction band. Okay. So in n-type semiconductor, if you take only n-type semiconductor, in the valence band also free holes available, that is very less compared to this. Suppose if you take n type semiconductor, electron density is much greater than hole density. Okay, if you take p type semiconductor, hole density is much greater than electron density. That's why only in n type semiconductor we are showing electrons only, and p type semiconductor we are showing only holes only. Okay, right? So now here, see, when you give some biasing voltage, plus and minus, so this plus voltage, positive voltage, push these holes towards the interface, because holes having plus charge, positive charge, and we are applying also positive charge. So these holes repelled by this positive potential. Similarly, the electrons in n-type semiconductor will repel by this negative potential, and these electrons also try to move towards the interface. Okay, try to move towards the interface. So electron will reach after certain forward bias voltage. Here also holes will reach after certain forward bias voltage, right? So after reaching here, these electrons will jump from conduction band to valence band. Okay, conduction band to valence band. So these electrons all will jump from valence band to conduction band and recombine. Once they recombine here, it will emit the photons. It will emit the photons. This is the mechanism of how the photons emitting in PN junction under forward bias condition. So here only we are applying forward bias condition. We are applying positive voltage to P side and negative voltage to N side. Because of this positive and negative voltage, holes are pushing towards the interface or junction, and electrons also pushing towards the interface and junction. At the junction, or at the interface, near the interface, these electrons from conduction band to valence band jumping, and after jumping, this electron hole recombination taking place. Once this recombination takes place, the excess energy released in the form of photons. Okay, this is what LED working theory, how these photons are emitting LED. This is the process. Okay, now question is, so why these electrons only recombining at the junction, why not other places? So suppose if you take here in the n-type semiconductor, here also there is a chance of jumping from conduction band to valence band, right? Isn't it?
Yes.
Similarly, here also, why it is not jumping in this place? Anyone please? So only why we are saying only electrons holes recombining at the interface and emitting the photons. So why these electrons are not recombining in only n-type semiconductor or only p-type semiconductor? There also electrons are there, downside also very few holes are there. Suppose if you take n-type semiconductor, holes are the minority carriers. So if it is 100 electrons are there, here maybe 10 holes are there, like that. Very few holes are there. But why this is not happening? Why we are not talking about this thing? What is the reason? What could be the reason? Anyone? Anyone please? So here what is happening here? See. So in this case, we are applying forward bias voltage, right? Most of the electrons are, there is a force behind these electrons. So this negative potential always pushing these holes towards the interface. One reason, that is one reason. And here also, this positive potential push these holes towards the always forward, this interface side. These holes are not staying here, they are not staying for long time. So this positive potential always pushing these holes towards the interface. Okay, that is one reason. One more thing, here also, if suppose there is a very less number of electron hole recombination takes place here, because here holes are the very minority carrier, very less number. Here electrons are very high number. Even most of the will push forward towards the interface, but some of the maybe will recombine with holes, but this is very less number. But this whatever after recombining, some photons will emit here also, but these photons again absorb in the same material. Okay, that's why these photons are not useful. Okay, what I said here. So if suppose if you take only n-type semiconductor, let's take only n-type semiconductor. I will draw here just for understanding. So here we have a n-type semiconductor, right? Similarly, like what we have this what would drawn in the band diagram. Here free electrons are there. Okay, free electrons are there. In the valence band also very less number of free holes are there, because in n-type electron density is much greater than hole density. This is electrons are the majority and holes are the minority carriers, right? So here there is a chance of recombination. Okay, once this recombine, here also photons emit, but these photons are density is very less. Okay, very less. Even though these photons after creating this photon, this will again absorb in the same material. Okay, same n-type material will absorb. So this will not come out from the surface. That's why this whatever recombination emitted photon due to recombination in the neutral region or bulk region, that is still after release also they will again recombine, again absorb in that material. That's why these photons are number is very less, and this less number also still that will absorb in the same material. So these photons are not coming out of the surface. That's why whatever here less number will recombine, less number photon will generate, but this is also not useful. This is also not useful, because these photons are again absorbing the same material. That's why only whatever photons recombining in the depletion region we are getting, we are absorbing. Okay, we are seeing that photons only, we are not seeing whatever here also. See, suppose if you take here holes, magnetic carrier electrons are there, very less number. There is a chance of these two recombination, but here also some photons will emit, but these photons again absorb in the same material. Okay, this will not come out of the surface. That's why we'll see very less. This is not useful. This whatever recombination photons emitted photon in the bulk region, it is no more useful. That is why only our active area is depletion region only. This is only our active area. Space charge region only our active area to emit the photons. Okay, this is the process of getting the photons. Very simple. We are taking PN junction, and in this PN junction we are applying forward bias voltage. So because of this forward bias voltage, holes will move towards the interface, and electrons from n-type semiconductor will move towards the depletion region. Once this depletion region is come, they will recombine. Okay, they will recombine. So we are giving potential, but this if you give potential, they have to see these electrons are seeing some barrier height. So instead of climbing that, they need more energy. That's why in the meanwhile they are losing that lifetime, so that they are coming again and recombining. So see here one more important point here. So we applied negative voltage to n-type semiconductor. Whatever electrons here in the conduction band pushing towards the interface. Okay, these are moved towards the interface, but at the interface electrons seeing some barrier height. Okay, this is the barrier height, and similarly holes also seeing some barrier height. Okay, instead of moving towards the other semiconductor, the lifetime is over. Okay, instead of this, they have to overcome this barrier, so they need more potential energy. So if they don't have much potential energy, they will not cross this barrier. So if they will not cross barrier, means they will stay sometime in the depletion region. So meanwhile the lifetime of the charge carriers will complete. So this will recombine. This will recombine in the depletion region. So why there is a why electrons holes are mainly recombining in the depletion region, means the reason is here when you give forward bias voltage, electrons holes are moving towards the interface, but to cross this barrier, they need more energy. They need more energy. Whatever they don't have much energy, they will stay for some time there interface because they have to climb. Okay, they have to climb. That's why they will stay some time. The meanwhile the lifetime of charge carrier will complete. So they will jump from induction band to valence band and recombine. So if you see here on example here, so there is a, suppose here one hill is there, hill is there like this. So you are going on bicycle or something like that. Okay, it is difficult to climb this one, or you will take more time to climb this one. But here towards downside, you will take very less time. Time is less here. So here also same thing. While climbing this barrier, the charge carriers will spend more time in this region. Okay, but downside it will easily come. So same thing here also happen, where the in the bulk region they easily move towards the interface. Once the charge carrier come to the interface, they will see some height. So to climb that height, they need some time. Okay, they need some time and they take some time. Okay, because of this time and during this time they will lose energy and they will jump from conduction band to valence band and recombine. Once they recombine, the excess energy will emit as a form of photons. In the form of photons, these photons will come out from the surface. It will looks like a different color or light. Okay, it will looks like a light, and that is what we see after LED lamp glowing. Okay, so this is the working of LED, right? So in the bulk region also recombination takes place, but less number of photons will emit in the bulk region. Again, these emitted photons also again absorbed in the bulk region, so that photons no more come out from the surface. That's why these photons are not useful. Only whatever photons emitted in the depletion region due to recombination of electron holes, these are coming out of the surface of material, and these will seeing a after glowing the bulb. Okay, that is the photons are useful. And whatever emitted photons in the depletion region or space charge region are useful only. Okay, is this clear to you after this theory how the photons emitting? Is this clear?
Yes, sir.
Okay, now one more important point is here. So in your just in regular life, you are seeing blue color lights and red color light and red color and green different color LEDs you are seeing, right, in your home or some functions, and decoration lights and designing. And if you see these signal lights, these are red, these are red. Suppose if you see in your TV monitor, sometime you will see blue screen, right, blue screen, or sometime you see green screen, or sometime you see, I think you have seen different color LED lights. That means what? Have you seen different color lights?
Yes, sir.
So some are white. Okay, some are white color, some are blue color, some are red color, some are green. Okay, these color, how these colors are coming from a LED light? Okay, how this color we are getting from LED bulb or LED screens? Okay, how these are getting? Any idea how we are getting different color from this LED lamps? Some white light, maybe red color and green color, blue, orange, whatever. In decoration lights also you are regularly see this color, right? When we see the Diwali festival or some other functions, will arrange on the walls. Okay, on the building will arrange these lights. Okay, sometime one of the light will come blue, one of the red, one of the green, like that. So how these different color is coming from LED? What is the reason how these are different color coming in the bulbs? What is the reason? What could be the reason, anyone?
Gas in it.
Okay, so if you take a tube light, okay, if you take tube light, we are filling some gas. Okay, this will ionize And on the gas tube, what we are doing, we are filling some phosphor coating. Here phosphor coating. Then whatever emitted light, we are coming only white. Okay. So this is in case of tube light, you can say we are filling gas. But here only taking semiconductor material for LED fabrications, whatever LED to making LED, we are only using semiconductors, only using semiconductor. These are solid material. It's not a gas. Okay. It's a solid material. It's not a gas. Okay. But tube lights are, we are light is coming from tube light due to gas ionization of the gas. But here, how we are getting here? You are using semiconductor material, but you are getting different color light from the these LED bulbs or LED lamps or LED screens, whatever. Okay. So what is the reason? So it mainly depends on material. Okay, mainly depends on what material we are choosing to fabricate the LED material. Okay, suppose you want blue color. What is the wavelength of blue color? Wavelength blue lambda. Wavelength of the blue color. What is the wavelength?
4.5 to 4.9.
Yeah, around 400 or 430 nanometer. In case of nanometers, this
10
is
power
the
of minus 7.
10 power of minus 4.
Minus 10 power of minus 7 meters.
Okay, okay. Whatever you can take meters or nanometers or micrometers, whatever you can take angstrom, you can take whatever convenient way you can take. So here about 430 nanometer for blue color. Okay, suppose if you take red, so this is about 600, about 650, something like that. Okay, about 650 nanometer. Okay, so if it is suppose LED is emitting red color means, so red color means it is emitting 650 nanometer light. Okay, 650 nanometer light is coming from the this waves or whatever you can say, waves or rays. Okay, this color, this wavelength is emitting LED. That means, so here we will do one small exercise problem. Okay, suppose you want a red color. So you want what material you have to use, how you will choose this material. Suppose lambda is given by, so how you will estimate lambda means wavelength means, okay, here formula is there 1240 by this Eg. Okay, if you take Eg in electron volts, here the wavelength will comes out of in nanometer. Suppose which material if you take, you will get 650 means. So here we have 1240, 1240, and if you take about 2 electron volts, if you take band gap of material 2 electron volts, you will get around 620 nanometer. 620 nanometer. So if you want a nearly red color, red, not exactly red, nearly red color, you have to use material of band gap 2 electron volts. Suppose this band gap 2 electron volts, then you will get the, suppose see here. So this band gap is 2 electron volts, and I am drawing directly. Okay. Here also this is 2 electron volts, and this is also 2 electron volts. P, N, N. We are taking 2 electron volt material and 2 electron volt material. Okay. So once we make these two semiconductors, here electrons will recombine with holes and emits the photons. Which color photons will emit? Here red color, nearly red color, because once you calculate this formula, using this formula, once you calculate wavelength, you will get 620 nanometer. That means red color. Okay, mainly here the conclusion is here, depending on chosen material, the photon color is changing or emitted light color is changing. Suppose LED, suppose you are getting blue color, suppose which color, which band gap you have to use here? Blue means about 3 electron volts band gap material. If you use, you will get the about something like that 410 nanometer light will emit from the LED. Okay, suppose you want blue color, so according to you have to choose the material. so that you will get only blue color from the LED lamp. So for that you have to choose the material which is having band gap of 3 electron volts, about 3 electron volts, then you will get the blue color. So this way we will choose the material and output will get the required color. Okay, required color. Okay, how LEDs are emitting different color. Did you understand now?
Yes, sir.
So mainly thing is here depending on band gap of material, depending on okay depending on band gap, or you can say material also. Each material having different band gap. Okay, material depending on band gap, the LED color will change. LED color will change. Okay, this is the main reason you use different material, you will get different color. Okay, depending on our requirement you choose particular material and you will get that color only, different color. Okay, this is the main way of getting different color. Suppose mostly the here will for LEDs, so photons emitting means which type of band gap material we have to choose, direct or indirect. Photons are emitting from LED. So direct band gap material will emit photons, or indirect band gap materials will emit photon. We were discussed yesterday also. Which band gap material will emit photons?
Both will emit, no, sir.
No, only
Direct, sir.
yeah. Okay, see here direct band gap material will emit photons. Okay, photons. And indirect band gap material will emit phonons. That is not a photons, phonons, phonon. Okay, the difference is here direct band gap material emit photons because excess energy emit in the form of photon. But here in indirect band gap, electron will interact with lattice. Okay, once this electron will interact with lattice, the mechanical waves or heat will be generated. Heat will be generated, or heat, or you can say mechanical wave, or this one we are calling as a phonon. Okay, phonon. So indirect band gap always phonons will be emitted. In direct band gap photons will be emitted. So from this we will always choose for LED materials direct band gap material. LED, for making LED, direct band gap materials are the suitable. Direct band gap materials are the suitable materials. Okay, direct band gap. Okay, these are sorry. This always we will choose direct band gap material. So direct band gap mainly compound semiconductors. Mainly compound semiconductors are direct band gap semiconductors. Okay, silicon and germanium are indirect. Okay, these are not useful for making LEDs. This silicon germanium is not useful. Okay, only direct semiconductor, that is mostly compound semiconductor like gallium arsenide or gallium phosphide or gallium arsenide phosphide. Like that, we will use this kind of material and we will emit the light. Suppose if you use gallium phosphide, okay, suppose if you use gallium phosphide, you will get the red color light, that is 700 nanometer, 700 nanometer, and also green color. You will also get green color. This is about 565 565 nanometer, 565 nanometer. So here see, if you use gallium nitride, why there is a two colors? So either you can get red color or green color. Why this is happening? Any reason? So we used only gallium phosphide, but here we can get red or green, whatever you want. So this will be changed. Suppose gallium is there, here phosphide is there. Suppose depending on percentage of this element, suppose this is 50% and this is 50%, that time this is different composition. Suppose this is 30%, this is 70%. So this is gallium, gallium phosphide. Okay, so like that, when you doping is changing, that means the band gap is changes. Band gap will change depending on percentage of this element. Suppose this is 40, this is 60. Depending on this concentration, depending on percentage of this element, the band gap will be changed. Okay, once the band gap is changing, the wavelength also emitted photon wavelength also changes. Okay, that is the reason here using gallium phosphide, but using different concentration of gallium and different concentration of phosphide, you can change the color of the LED. Okay, that is one more thing. And gallium arsenide phosphide. Okay, gallium arsenide phosphide. Using this one, you will get yellow and yellow, yellow, red. This color is like yellow is about 585 nanometer. 585 nanometer. Red is like 700 or 650, above 650 nanometer. Using gallium arsenide phosphide, you will get these two colors. Okay, again same, depending on doping of this element, doping percentage of this element, the band gap of the compound semiconductor will change. Once the band gap is changed, the emitted photon color is changing, right? We have solved the problem, right? 1240 by EG. Okay, if EG is changing here down, the after resulting wavelength will also change, right? Resulting wavelength increase or decrease depending on this band gap, the wavelength will change. Wavelength is changing means color is changing. Okay, band gap just because of composition. Here gallium arsenide phosphide, three elements are there. Depending on this composition, suppose this is 10%, 30%, this is 60%, or 40%, 10%, 50%. So percentages, depending on this composition, the band gap will change. Once the band gap is changed, the wavelength will change. Wavelength is changing is nothing but color of the emitted photons is changing. Color of the emitted photons is changing. So one more thing, gallium nitride, GaN. Using this one, you will get gallium nitride. Blue color you will get blue. Okay, this is blue, about 480 nanometer. About 480 nanometer. And gallium arsenide. Gallium arsenide. Using this one, you will get the IR, like IR radiation. This is about 900 nanometer. So mostly, which range we are seeing LED lamp? VIBGR, right? What we are seeing
Yes, sir.
colors? VIBGR. VIBGR. Okay, this is visible spectrum. What do we call this one? Visible spectrum. So our LED lamp should always emit like about 350 to 800 nanometer. 350 to 800 nanometer. This is useful spectrum. So always choose the material to emit this color, this wavelength. Then accordingly, this wavelength range, we will choose the material for fabricating LEDs. Okay, suppose here if you use gallium, so here we have seen some example. If you use gallium phosphide, red color, green color, this is in the visible range only, 700, 560. So if you use gallium arsenide phosphide, you will emit yellow, red. That is also 580 and 700. This is also visible range. If you use gallium nitride, blue photons will emit, that is 480 nanometer. Okay, if you use gallium arsenide, this is about 900 nanometer, nearly near IR. This is near IR wavelength. Okay, so IR is 900, 852, like something like 3500 nanometer. So depending on our color requirement, we'll choose the material. We'll choose the material. That is the main important thing. Okay, so and one more thing, mostly we'll see visible spectrum, that is violet to red color only we will see. We don't want IR light, but where you need application of IR light, you can use the gallium arsenide, something like that. Okay, the color of the photon, here see two things. First, PN junction, these LEDs are just PN junction diode. It will convert electrical energy to optical energy when you connect forward bias condition or under forward bias condition. So in forward bias condition, holes in p-type semiconductor move towards the interface, and electron in n-type semiconductor move towards the interface. At the interface or space charge region, this electron hole recombine. Once this recombine, it will emit the photon. Okay, that means it emits the light, or you can say, okay, this light color will depend what material, depending on material, this light color will change. Okay, different material having different band gap. Okay, once we have solved, estimated the wavelength of this material 1240 by band gap of the material. So using this estimation of wavelength, we can choose the different material depending on our requirement. Okay, this is the way of emitting the different color light from the LED lamp. Okay, so is this clear to you up to now what we have discussed up to now?
Yes, sir.
Hmm? So suppose we have silicon material, here band gap is what? 1.12 electron volts. So now if you solve this 1 lambda, okay, 140 by 1.12. This is about, turns out about 1100 or 10,000 something, right? 1100 nanometer, 1100 nanometer. So this is IR light. If you use silicon material, you will get the IR lamp, IR light from the LED. Germanium is 0.65 electron volts. So if you use this lambda, same formula, 1240 by 0.65, it will also come around 1300, about 1350 something like that. Okay, 1350 about this wavelength. This is not exactly. Okay, about 1300 or 1400 nanometer. This is also IR light. This is also IR light. That's why we don't see IR light. With human eye, we cannot see IR light. That's why using silicon germanium, LEDs are not fabricated. Only most of the LEDs are fabricated using compound semiconductors. Okay. So this is the theory of how photons emit, how the photon color will depend on different material we have studied now. Tomorrow we will see construction of LED and IV characteristics. Okay. So if you have doubts, you can ask me. Otherwise, we will close the meeting.